Morning, everybody. It looks to me like bienvenue tout le monde. C'est vraiment très encourageant qu'il y ait tellement de monde ici dans la salle, puisque nous sommes toujours de bonne heure. Earlier than yesterday. So in any event, I would encourage those of you who are in the far reaches of the room to move up here if you'd like to do. We have just one table here for speakers and VIPs, but I think we're all VIPs here today, so if you'd like to do, please move up. I'm coming from the Talent Meets Market breakfast that we've just had. The talent part is the young people who are registered here, and the market is the older folks who are also part of the breakfast, who have had something of a career path, and the students and the working professionals come together at this breakfast, which is a feature of every CASI conference. And we have an informal meal together early in the day, and we chat, and the students find out about what working professionals do for a living. The question often is, how can I work at your company? And that's fine. The answer usually is, well, we have an HR department. Do you have a CV? Some students come with CVs. They have business cards, a lot of them. So it's a really good event, and I'd encourage those of you who are lucky enough or devoted enough to come back to our next CASI conference. We're actually having a space one in a month from now in this hotel, to think about participating in the Talent Meets Market breakfast on the space side of the CASI house. Today, I'll just run through the program. We have two plenaries. A plenary starts the day today in just a few minutes from now, the hybrid electric propulsion plenary. The panelists will be introduced by the General Chair of AERO 2019, Eric Laurando, who's here right now. The lunch today, there is a lunch today. It's a lunch oriented to members of CASI. It's our annual general meeting, and it's going to happen in the Chomedey room where the Talent Meets Market breakfast was, from 12:15 to 1 o'clock. So all CASI members are welcome, and I would encourage you to attend that AGM if you're a CASI member. Tonight, the Senior Awards reception and gala dinner takes place. It will be a gala event. We'll be recognizing the recipients of all 5 of our senior awards. It'll be a fun evening. There will be lots of people, I think, in attendance. It'll be particularly well attended by our colleagues from Bombardier and Airbus, because Bombardier is sponsoring that meal, and also because several recipients of senior awards are staff of Bombardier. A couple of housekeeping remarks. First of all, first of all, there is a typo in the program that's been pointed out. Tomorrow, if you look at the back of your program, you see that there's program at a glance. You can believe this. When you look in your program and you look at the technical session page for session 7, you will notice, and you won't be able to see it from here, so I don't know why I'm trying to get there, but I'll just refresh my own memory. Up here at the top, it says that the technical session follows the lunch. This is not the case. The 2 technical sessions tomorrow morning will be back to back, and then the lunch takes place. One other follow-up to the plenary keynote yesterday that Dr. Rothblatt presented with such impact, clearly, from the comments I've heard. Several people have asked if I know about how her daughter has fared. The answer is, when Martine first identified this problem with her daughter was about, I think, 6 years old or 8 years old, quite young. It is now 15 years later. At lunch yesterday, Martine showed us on her phone a video of her daughter with whom she had spent the night before in New York City at a gala event. Her daughter was dancing with a robot, which is kind of a typical thing for Dr. Rothblatt's life to be consisting of, is a daughter dancing with, something mechanical. Anyway, her daughter's doing, doing just fine, living life and loving it, not going up and downstairs, not participating in any sports, but she's doing just fine. So for those of you who were wondering, that's the answer. So at this point, Dr. Laurendeau, if I might bring you up here to introduce the panel. Thank you.
Good morning, all. I'll just take 3 minutes of your time, but these are important for me because the advisory board split the work for the panelists, and I was in charge of mounting the hybrid electric propulsion panel. And I had 3 names in mind, and I'm so happy, and I thank you, to accept the invitation because it's really an amazing panel we have, and my first top 3 choices just said yes. So I'm grateful for your positive answer. So I encourage you to go and see who these people are because we have top-notch people. So we have David Rancourt, who's going to be chairing the panel. And I'll just like to note that he graduated from Dimitri Mavris Group at Georgia Tech with Professor Dimitri Mavris. And we have Dr. Askin Isikveren from Safran, but the previous person working at Bombardier, who I've had a chance to work with, and he's on NATO committees on electric initiatives. And we have Philippe Novelli from ONERA, who sits on the alternative fuel group from AERO, which is a huge European framework for research in aeronautics. And we have Sylvain Larochelle, who comes from very far away in Longueuil, from Pratt and Whitney, Canada, who sits on the board of Garden. So these are very people that play a leading role. So thank you all. So from now, without further ado, I'll just pass it to David Rancourt, the panel chair. Thank you.
Thank you. Bonjour à tous. Good morning, everyone. Thanks for being here today at 8:30 a.m. So I'm a professor in mechanical engineering and aerospace engineering at the Université de Sherbrooke, not too far away. And as Eric mentioned, when I saw the names of the panelists that we have today, I was really, really happy to see that they all accepted. So we know a couple years ago, nobody thought about putting electric motors and batteries in an aircraft, right? And now we have prototypes flying around. So hybrid electric has made a long way since it's the first studies that happened. So today, the 3 panelists we have, without any further delay, let me introduce first Mr. Philippe Novelli from ONERA. Philippe graduated from Spiro High Engineering School and joined ONERA in 1990. He has successively worked in CFD for combustion, system design, and analysis for innovative propulsion systems, alternative fuels, project management, as well as research coordination and development. Philippe Novelli also spent 3 years at the Environment Directorate of ICAO, where he was responsible for alternative fuels in the context of cooperation between ICAO and European Union. Philippe Novelli is now Program Director for Aeronautic Propulsion and Environmental Impacts at ONERA. So what we will do is each panelist will present for about 10 to 15 minutes on their vision and perspective of hybrid electric propulsion, and then we'll open up questions for the audience. So Philippe, I'll invite you to come here. Thank you very much.
It's not the right presentation. Yes, it's a presentation of Askin. It's not mine. No, I would prefer not. Okay, that's the correct one. Okay, so thank you. Good morning, ladies and gentlemen. Maybe I will say first a few words about my organization, ONERA. How do we? It's this? Okay, sorry. So just to introduce ONERA, ONERA in fact is the French National Research Center for Aerospace Research. It was created just after the Second World War, and so we have been pursuing research for now for more than 70 years. And we have a workforce of about 2,000 people with a budget above 230 million euros per year. And we are covering, in fact, all fields of aeronautic research, including defense, aeronautics, and space, with a large coverage from physics to system analysis, including aerodynamics, radars, energetics, and so on. So it's quite a complete organization. And we're also a major actor in Europe for wind tunnel. You may probably know our large wind tunnel in Modane. One of them is maybe the largest wind tunnel in the world. So the focus of my presentation will be in fact on one aspect of hybrid electric propulsion, which is more related to commercial aviation. And the first question is, why looking at hybrid electric propulsion for commercial aviation? And I guess you have already seen this famous curve on the left, which comes from ICAO, and which shows that due to the increase of the air traffic, the anticipated progress on aircraft technologies will not be enough to compensate the increase of commercial aviation emission. And we will not be able to reach the goal of ICAO countries, which is to stabilize the emission at their level of 2020. So there is what is called a technology gap, which means that conventional technologies, including open rotors, are not able to reduce emissions, and so we need to consider other solutions. So it can be offsetting our emissions, it can be alternative fuels, and it can be disruptive technologies. And there, obviously, you could say, well, we can try to do electric aircraft as people are doing for cars, but unfortunately, the projected performance for batteries do not allow to envisage commercial aircraft, fully electric commercial aircraft. I've put here some figures which comes from NASA, in fact, which give you some order of magnitudes of what is required to do an electric commercial aircraft. So you see that with 500 watt-hour per kilogram as energy density of a battery, you may envisage a regional aircraft with only 200 nautical miles of range, and that to consider a 100 pax aircraft with 900 nautical miles range, you would need to go beyond 750 watt-hour per kilograms. And for the time being, from what we can see from different sources, beyond 600 watt-hour per kilogram, there is no clear way identified today. So we cannot consider to do electric aircraft in a predictable future. At the same time, the curve on the right shows that if we want to address aviation emission, we need to look at large aircraft. This curve, in fact, gives you the ratio of the total fuel burn that is represented by the different range of flight, of commercial flight. And you can see that if you want to address at least 40 or 50% of the total aviation emission, you need to look at small, medium-range aircraft. And so you need to find solutions for these aircraft. And that's where hybrid electric propulsion is envisaged today and is studied by many different entities. So what is hybrid electric propulsion? In fact, in the most general sense, it's mixing a thermal sources, a turbine engine, with some electric sources, some electric engines. You have many different solutions. You have some illustration here on the right. It can be parallel, what is called parallel hybrid. It means that you put some electric assistance to a turbine engine. It can be the total opposite, turboelectric, where you produce electricity on board from a turbine, but then your motor that drives the propeller is electric. Or it can be a mixed, called series hybrid. Something very important to understand is that hybridization does not bring any benefit per se. It does not per se increase the propulsive efficiency of the aircraft. At the contrary, it increases the mass. So you see that there is a kind of intrinsic difficulty there. And in fact, the benefit you can expect from hybrid propulsion is only through the degree of freedom that it provides to optimize the aircraft. So you need to go to a different way of designing your aircraft. And there are many options for that. And I will present a few examples on the next slide. So it's difficult to have a rigorous categorization of the different types of hybridization that you can find. These are just examples. So a first solution that does not induce too many change in the way you are designing the aircraft is to bring electric assistance to a turbofan or turboprops. So the idea there is that you optimize your engine for cruise in order to have the best efficiency, and then you provide some electric boost in some phase, for example, takeoff and climb, in order to provide the required power. This is typically a parallel hybrid. So it has been studied by different organizations. And typically, the associated electric power is in the range of 2 megawatts. So it's not that far from the maximum electric power that we can find on Boeing 787 today, which is about 1 megawatt. The figures that we find in the literature for the benefits for the block fuel reduction is between 5 and 14% for mission, typically in the range of 900 nautical miles. What we have to be careful with all these figures that have been provided today is the assumption behind, especially with the batteries. And also we need to be careful that in that case, you may reduce block fuel, but maybe not block energy, which means that there may be some substitution effect from energy stored in the batteries, and then you reduce emission, obviously, only if this electricity that you use for the batteries is from sustainable sources. It's exactly the same dilemma as for electric cars, no difference there. Another solution that is studied, in fact, shows another way to take benefits of hybridization, which is creating a synergy between propulsion and the airframe. And this is a solution using a tail thruster that ingests the boundary layer of the fuselage in order to increase the global efficiency of the aircraft. So the typical example is a Stark EBL from NASA, and there is also a study currently in Europe with the center line. There also the electric power is in the range of 2-3 megawatts. And from NASA study, benefits could be up to 8% on 3,005 nautical mile missions. We can go further and use the hybridization in order to optimize the distribution of the propulsion of the propellers on the aircraft and create synergies with the airframe, in fact. So you have, for example, here on the right, it's a configuration studied by DLR in which they use hybridization to have a wingtip propeller in order to reduce induced drag, and also to control the aircraft so that they can reduce the size of the tail and so improve the mass of the aircraft. You have a solution which it's more disruptive, which is massively distributed propulsion. So you have an example here with this ONERA Safran study of a commuter, in which, in fact, you use distributed propulsion to blow the wing and so increase the lift at low speed, which allow you to size the wing for cruise and so reduce drag, reduce mass, and so make some benefits. And you can also use massively distributed propulsion in order to increase the effective bypass ratio of your turbine engine, or reduce it at the same time reducing the fine pressure ratio to increase propulsion efficiency. So this has been studied, for example, by an American company with the Eco 150 on the left, which use 16 ducted fan on the wing, with then a total electric power which is in the range of 20 megawatts. So they obtain something like 11% fuel burn reduction. We are studying at ONERA something similar with the Dragon configuration, where there we have 24 megawatts of electric power. And something important that is especially true for the Eco aircraft is that to deal with such a power, you need to increase the electric voltage of your system. So, for example, in the Eco, they are going up to 6,000 volts, which give you an idea of the associated challenge. And the most extreme example is the one from NASA, which mixed both distributed propulsion and boundary layer interaction with also superconductivity, and for which they obtained something like 20% emission reductions. So from this overview of examples, you can see the challenge associated to hybrid electric propulsion, which is first the fact that currently we are not sure of the configurations that best benefit of this type of technology. You will still have to identify the good design of the aircraft. You see that there are also many uncertainties still on the prediction of the performance, which depends on the level of fidelity of the tools that are used to assess this configuration, on the technical assumption also. And something which is clear is that you need to make studies at the right fidelity level, because you see that it's optimization. You need really to optimize everything, and so for that you need to have high fidelity. And obviously we have many challenges at technology level. You could see that it's unprecedented electric power for an aircraft, and if we go for the most extreme solution, if we go to 20 or 30 megawatt on an aircraft, it's tremendous. This goes with a tremendous increase of voltage on an aircraft. You see studies with 7 kilovolt. So this induces obviously problems of electromagnetic interference, arcing problem potentially, also thermal management problems, which are quite different with, compared to what we have with conventional system, because there we have a large source of heat, but with a low temperature, which makes the cooling more difficult. Obviously, we need to increase drastically the density, the electric power density of the electric machines. The same for batteries. We need to increase electric density. Maybe there is a need for superconductivity. That's something questionable. And obviously, there will be a lot to do with certification, because we are in a completely new world there. So, as a conclusion, you see there is still a lot to do at technology level, but also to confirm the benefit. And from what I've presented from the literature, the benefit, you could say, is not that big. But we have to consider, to be careful, because we compare this benefit to current technology projected to 2035. And so it's not done to obtain this level of performance for the conventional technology in 2035. And there will be a lot of effort required to do that. So we should be careful when comparing the two solutions. And also, conventional technologies, they are at the final phase of the S maturity curve, where these technologies are just at the beginning. So we have more rooms for improvement in the future. As you saw, it may induce a complete disruption in the aircraft design, with the propulsion architecture, which is closely linked with the general aircraft configuration, and which requires really a strong integration and maybe some change in also in the industrial organization, where is the boundary between airframe and propulsion. That's maybe a question. And a last point for the conclusion is that we can see that this will not solve all the issue of aviation emission by itself, because if we are still using fossil fuels, this type of system still use thermal engines. So we will not completely eliminate CO2 emissions. Also, the question for long-haul aircraft, already for small, medium range, the electric power is tremendous. So for long-haul aircraft, it's questionable. And so this is certainly something we need to study. This is something clearly new and of interest, but we need also to continue looking at other solutions, and in particular maybe low carbon fuels, maybe hydrogen, who knows, in order to really address the problem of aviation emissions. Thank you.
I would like now to introduce our second panelist, Monsieur Sylvain Larochelle from Pratt & Whitney, Canada. Sylvain joined Pratt & Whitney, Canada in 1999 as an industrial maintenance manager. He assumed positions of increasing responsibility in manufacturing, operations, and supply management, as a machining strategic sourcing manager at Pratt & Whitney. He started his current role in January 2016. Sylvain holds a bachelor's degree in mechanical engineering from Royal Military College in Kingston and a certificate in law from Université de Montréal. He is also chairman of the board of Centre de Technologie Aérospatiale, CTA, in AERO 21, a board member of Green Aviation Research and Development Network, GARDEN, AERO Montréal Innovation Workshop and Technology, and Innovation Committee of Aerospace Industry Association of Canada. Sylvain Larochelle is now the Technology Collaboration Office Manager, Engineering at Pratt & Whitney, Canada.
Bonjour à tous. Good morning, everybody. Exciting time for us at Pratt Canada, at UTC, and obviously related to this hybrid electric propulsion topic. Across the next 15 minutes, I'll essentially share three main elements. How Pratt Whitney Canada is positioned within the UTC ecosystem and the magnitude of transformation in 2019 within UTC. Our perspective from a Pratt Canada standpoint on hybrid electric propulsion. And finally, some elements of standardization and certification that obviously as industrial members we're quite concerned with and that we're currently working on. So starting with where is Pratt Canada positioned within UTC? Well, for some of you, it obviously has been public for quite a while, but UTC is going through the exercise of splitting some of its division. So by early Q1 2020, we foresee that UTC moving forward will be an aerospace-centric corporation. So both Otis and Carrier divisions will essentially be standalone enterprises with their own respective board. So that really enables us to focus from a corporate standpoint really on aerospace. So as you can see on the top left of the slide, so Pratt Canada, we're one of three divisions of Pratt & Whitney, working now very closely with our colleagues from what we now call Collins Aerospace System. Collins Aerospace, which essentially is including what we used to know as Rockwell Collins, Hamilton Sundstrand, and Goodrich Aerospace, which combined were forming UTAS, United Technology Aerospace System. So UTAS has now become CAS, Collins Aerospace System, with the full integration of Rockwell Collins. Essentially, from a system standpoint, covering most of systems on board an aircraft. In line with this, our UTRC Research Center organization located in East Hartford will moving forward focus solely on aerospace research work. So is the newly formed division of UTAP, United Technology Advanced Prototype, which also will focus essentially on aerospace projects. So as you can appreciate, a significant transformation for us. At this point in time, there are more than 500 full-time people working in this overall split. UTC has activities across 120 some countries, so you can imagine all the fiscal, legal, and related elements to manage this year, thus such a significant takeover. Now, as a aerospace-focused corporation, let's step into the notion of hybrid electric. So for us, the notion of hybrid electric from a market standpoint, we tend to split this overall market essentially in three major segments. A very short-range segments, which now creates a brand new market in evolution. Some would call it urban air mobility system, unmanned air taxis, whatever. So there's a lot of acronyms around this very short range. And as I said, it's a brand new market in evolution. We consider this market essentially as fully electric, powered. Stepping into the middle of the market, we look at short ranges. So essentially general aviation, a regional turboprop, most of which will have a very short range as we look into the hybrid electric propulsion standpoint. And finally, on longer range, there's a notion of mildly hybridized propulsion system that could be leveraged. It is our belief that the original market that will essentially introduce hybrid electric will essentially be on the short general aviation side. As an example, Harbour Air has recently publicized the fact that they will fully transform Beaver aircrafts on the West Coast as fully electric. So that's also regulated by Part 23 certification. So that's essentially where we believe that the hybrid electric or fully electric aspect will be introduced from a market standpoint. Now, how do we address from a propulsion system those various market segments? As I said earlier on the previous slide, the notion of urban air mobility, we believe, will essentially be fully propelled by electrical power. So obviously, this notion is limited by the efficiency and size of the battery. Moving on to the short range, we believe that one option would obviously be supported by serial hybridization, where we take a thermal engine that essentially supports a generator, and we can distribute electrical motors across the wings and airspan, so we can then introduce a notion of distributed propulsion. So this is really where we start to integrate elements of generator, propulsors, inverters, control systems. So quickly, the sum of systems quickly goes up, so does the weight. And finally, for potentially longer range and also a different architecture, we're looking at parallel hybrid, where essentially we mount an electrical motor, we mechanically link a mechanical motor to an existing turbine, thus the notion of parallel hybrid, which obviously has another set of advantage. In fact, we can definitely use this electrical motor to support specific points in any given mission, whereas on the serial hybrids, essentially the notion of hybridization is involved across the full mission of an aircraft. So different benefits, different challenges, different architectures, supporting obviously different markets. So looking at this, going back to how we can undertake such a different and radical architecture change, we then go back and look at how can we approach this as a UTC. Well, essentially, Pratt & Whitney, as we saw on the corporate slide, focuses on commercial and military application. So for a larger commercial application, the notion of mildly hybridized airliner takes place, mainly supporting a parallel architecture in terms of hybridization. Collins Aerospace is obviously specialized in all the elements of motors and drives, so that's obviously that division which will essentially take care of those components. As a point of note, the 787 is extensively leveraging electrical actuators and components, and essentially Collins Aerospace is in the midst of those systems. And finally, from a Pratt Canada standpoint, considering our typical market segments, we're essentially open and supportive of both architecture, whether serial or parallel, and obviously we're focusing on both of those as we speak. Now, translating those architecture, translating how we can look at this from a corporate standpoint, we've recently publicized and came public with a project by the name of Project 804. So for those that are not familiar with 804, that essentially is a straight line between Montreal and Rockwell, Illinois. If you Google map those two cities and you draw a straight line, you will essentially understand that the distance is 804 miles. So that's where essentially the code name Project 804 comes from. It is also owned and supported by our newly created division, UTAP, so United Technology Advanced Prototype. So what we did essentially is that we've purchased a used Dash 8 that we intend to convert and essentially convert the starboard propulsion system from a typical thermal arrangement to a parallel hybrid electric. This whole notion and project is targeting to be flying by end of 2022. Unfortunately, I'm neither a UTAP spokesperson nor UTAP representative. So when the question period will come, unfortunately, I will not be able to take any questions specific to Project 804. There's already a fair amount of public information available on that, and I will obviously focus and answer questions related to our Pratt Canada perspective of hybrid electric. Now, moving on to the notion of standardization. So obviously, there are many elements of standardization that are stemming from a different architecture in hybrid electric. So we indeed need to define those various notions of mildly hybrid, parallel, serial. It is fairly high level understood, but when it comes to really defining those standards and systems, we're going to need to further push how accurate we segregate those various architecture. There are elements of reliability and redundancy that we understand today based on our set of parameters that will need to be redefined. A notion of heat management, and this is where, when I was talking earlier about serial hybrid, adding batteries, generators, battery control systems, inverters, all of those systems may or may not work at similar operating temperatures. When it comes to managing the heat and operating temperature of all those systems, the notion of standardization becomes critical. Not obvious to have all those systems working at the exact same operating temperature. Actually, it's a challenge. So for us, we don't obviously want to end up with 5 different heat management systems. It will only compound the weight challenge. So there's a lot of aspect of trying to standardize some of those components from a operating temperature standpoint. And finally, the notion of electrical, mechanical, electromagnetic interference and compliance is also an element of standard that we're obviously concerned and working on. Zooming in on the engine aspect, so what we used to know as the thermal engine. So the certification requirements for propulsion device will also need to be established. Propulsion device can take the shape of electrical motor in a distributed propulsion standpoint, so the notion of certification for those obviously needs to be defined. The notion of power rating and system rating. Today, we have a mechanical rating associated to our gearbox and a thermal rating associated to our turbo machinery. Tomorrow, the notion of rating on batteries, motors, control systems will also need to be defined. So related to this, power management standards at the engine level and aircraft level will need to be defined. And should we get into the urban air mobility, the notion of noise from a social acceptability, from a challenge standpoint, well, obviously those will need to be also addressed from a standard standpoint. So, leaning towards the conclusion, so can we say today that a parallel hybrid turboprop is a multi-engine aircraft? As I said earlier on Project 804, we will have a parallel config with an electrical motor mechanically attached to a thermal engine. Does that constitute redundancy in itself? Well, those are obviously some of the questions we're looking at. In the case of distributed propulsion, well, many electrical propulsors across the wingspan, how will this affect, the lift? It could essentially be, lifting, just activating the propulsors themselves will contribute to the lift. How will that, impact the requirements of the aircraft? How are we going to manage the notion of life-limited part? Today, especially in our hot section, we stress our material to a significant extent. So the notion of a life has to do with a full cycle: takeoff, cruise, and landing. Logbooks are very important in this perspective as we understand the amount of cycles our life-limited parts are going through. Tomorrow, trying to apply this to a battery or other electrical systems will then need to be defined from a certification standpoint. And finally, how will the energy left in any given battery be accounted for in terms of reserve versus today's situation where it's quite easy for us to understand we can burn X amount of fuel and obviously keep some as a reserve. So that notion of requirements and certification will also need to be addressed. In conclusion, for us, the regulation structure will obviously impact the way we will comply in our design systems, in our program management. So this is a fundamental reason why we're focusing on understanding those. And we want to prioritize standards that will facilitate the interfacing of various systems. We believe within UTC, looking at the complementarity of all our divisions, we're well positioned to work on this aspect of standardization and eventually work with our counterparts from the sector and the certification facilities to establish such standards. So that essentially concludes how we at Pratt, within the UTC ecosystem, are looking at the hybrid electrical propulsion new market and how this links to the notion of standards and certification.
Very intéressant, merci. Thank you very much. So our last panelist is Dr. Askin Isikveren from Safran. Askin's 28-year career comprises a broad range of technical specializations executed in industrial, academic, and research institute environments. His posts have included manager of advanced studies, both in industry and academic, senior academic, senior expert in the industrial sector, postdoctoral researcher, flight planning lead, and propulsion control and fabrication. After joining Safran Group in November 2015, he served as head energy efficient aircraft architectures, energy and propulsion department at Safran Tech, and until January 2019. Askin's previous employer have included American Airlines, Bombardier Aerospace, Harker de Havilland, SAB, and University of Bristol. His research focuses on advanced aircraft conceptual design, hybrid electric propulsion, distributed propulsion, innovative composite cycle engine architectures, and active aerostructural control design. He previously was an expert in contributor to the EC Roadmap Working Group, Transport, Electrification, and Aeronautics. He currently serves as an AIAA Aircraft Electric Hybrid Electric Power and Propulsion Working Group member and co-chair in NATO Science and Technology Organization Working Groups. Since September 2015, he has contributed as a program committee member of the International Council of Aeronautical Sciences and has served as an editor-in-chief of the Aircraft Engineering and Aerospace Technology Journal since 2009 with the Emerald Publishing Group. I'll invite you, Askin.
Good morning, everybody. I find myself back in Montreal very happily. As was mentioned previously, I had the pleasure of working within the aeronautical sector early to mid-2000s and had a very close association with Cassie as well, which was most fulfilling. So I remember those days with a lot of affection and fondness, and it's great to see a few familiar faces and hopefully meet a few new ones today. Okay, so my duty today is to discuss hybrid electric propulsion with you. And what I'm going to offer you, somewhat philosophical, but also we're going to delve into some technical aspects when it concerns this particular technology. See if this works. Now, before I go into the technology, I've had a good almost 3 decades working in the aerospace sector. And what I'd like to share with you, if you could allow me to wax techno-philosophically for a few moments, I'd like to share with you my perspectives when it concerns the implementation of new technologies within aerospace. It could be applicable to other sectors as well. And although we need to wrestle with certification, we need to wrestle with concerns, financial risk when it concerns suppliers, I feel there are 4 fundamental tenets that need to be fulfilled before we adopt any technology, regardless of it being hybrid, electrical, or otherwise. The first thing is that although the technology that we want to implement doesn't deliver its peak performance attributes, the best that it could possibly attain, we need to ensure that that said technology provides a solid business case. If there is no business case, there is no technology. Doesn't matter how wonderful, how fascinating the technology is, we need to foundationally have a solid business case, a solid financial rationale for it. So one example would be the more electric aircraft, as we've seen implementation on the 787, the Boeing 787, and other aircraft subsequent to that. Secondly, if we have a technology, we introduce it to the market, and it's got a solid business case, i.e. it's profitable for the company, the supplier, we need to ensure that technology has room for improvement over time. There is no use having said technology reach its peak performance capability and simply asymptote or stay at that level as other technologies evolve over time. Historically, it's been shown any technology that has a propensity of improving, let's hope significantly over time, will ensure longevity for that technology. Case in point, the dual Brayton cycle, the gas turbine engine. The third aspect is scalability. Any technology that's implemented must be scalable. And when I talk about scalability, I'm not necessarily just simply implying a linear scale of dimension. I'm talking about applicability as well. I'm talking about applicability of that technology on different aircraft platforms. So, for instance, if I have a tenure at Boeing and I work on a given technology with fixed wing commercial aircraft, short to medium range, wide bodies, etc., and then I decide to make a shift over to, let's say, Pilatus, working with very light executive aircraft, the knowledge that I employ, the technology that I deal with at Boeing should be easily transferable in the context of Pilatus. If you can achieve that sort of status for the technology, that is another reason for the aerospace community adopting that technology. The fourth aspect is synergy. As we know with aeronautics, if we look at the classical Breguet equation, the trade-off between gross weight versus airframe efficiency as well as propulsion, overall propulsion efficiency, we have these sometimes conflicting aspects trading off against each other. It is of utmost importance that technology that you're entertaining can have some potential to ameliorate or improve the performance of other systems, components on board the aircraft. So it is very, very important that we capture aspect of synergy. So one example that was given by Philippe was the AERO propulsion side of things, combining hybrid electric together with AERO propulsion, boundary layer ingestion. Now, I don't want to do this ad nauseum, but if we quickly have a look at the different types of architectural approaches that we can entertain, and this is according to the US National Academy of Sciences and Engineering, essentially we've got 6 domains, if you want to think of it that way. The first one is the series hybrid, where essentially we have a dedicated electrically driven propulsive device, and its source is electrical in nature, whether electrochemical or it could be through some sort of energy carrier like liquid hydrogen for purposes of a fuel cell. The second one is a parallel hybrid. What we have essentially, again, an electrical source, battery, fuel cell, and instead of an electrical node as we have in series, where we go from the battery to the electrically driven propulsive device, what we do is we mechanically connect that motor to, let's say, the shaft of a gas turbine engine, and we refer to that as parallel. Now let me highlight to you, hybrid infers electrical source that is electrochemical in nature or through some sort of energy carrier that we use for a fuel cell. Now, of course, we can do combinations of those. We could do a series parallel arrangement when it concerns hybrid electric. The zenith of hybrid electric is what is referred to as all electric. So we have no thermal engines providing motive power. We have no thermal engines converting mechanical to electrical energy. What we have is simply an electrochemical source, or let's say an energy carrier with fuel cell, providing the complete amount of non-propulsive and propulsion-related motive power for the aircraft, and we refer to that as all electric. Now, another set of domains here is what's called a turboelectric. We have a thermal engine. If we completely convert the mechanical power from the shaft into some useful electrical power, we refer to that as a full turboelectric. If, however, we decide to partition the motive power used for flight into one provided by the thermal engine, but also at the same time, some aspect of that shaft power is converted into electrical power via a generator, we refer to that as a partial turboelectric. Now, of course, we could play games and we could do even further elaborations. We could produce a series hybrid partial turboelectric arrangement where we would introduce, let's say, a battery into the scheme. So there are many different combinations that we can generate as a result of these 6 domains. Now, when we talk about hybrid/electric propulsion, fundamentally there are 2 non-dimensional parametric descriptors that are of greatest importance to us. One is referred to as a degree of hybridization for useful power. When I use the word useful, I'm inferring the power generated, delivered by the propulsive device, i.e. the drag power of the aircraft, if you want to think in those terms. And what we do is essentially we divide the useful power delivered by the electrically driven propulsive device by the total useful power that the aircraft generates. That's called HP use, degree of hybridization for useful power. The other category is degree of hybridization for supplied energy. And it is described as the amount of energy supplied from a given electrical source, electrochemical or energy carrier in nature, divided by the total supplied energy of the aircraft. So if we have a hybrid electric arrangement, the total supplied energy would be a combination of kerosene-based as well as, let's say, electrochemical-based. Now, these 2 seemingly simple parameters can define a whole host of different architectural options that I described to you a moment ago, i.e. HP use equals 0, HE is equal to 0, would be synonymous with our conventional gas turbine. HP use equal to 1 and HE equal to 1 would coincide with what we refer to as all electric. Now, with these parametric descriptors in tow and with much more algebraic elaboration, what we could do is produce generalized trait studies, and this could allow us to decide which could be the best architectural option for a given application, a given aircraft platform or given mission role. Here is an example that I show here for unmanned aerial vehicles or drone type applications, essentially. And what we do is we compare various parameters. So before we elaborate what the architecture should be, we would perform generalized trait studies. We would look at the relative attributes of an unknown yet undefined architecture and see what would be the best course of action. And I highlight it might not necessarily be strictly one given architecture. It could be a combination of the 6 domains that I talked about as well. And if we look here to your left, we have a series of figures of merit, metrics associated with state-of-the-art. If we look at a drone application here or unmanned aerial vehicle application, and we can see that if it's thermal engine alone, we have something like 25% overall power plant efficiency. But if we compare that to, let's say, the battery-based chain, which is something like 52%, we can notice straight away the overall propulsion system efficiency can be boosted by virtue of adopting this series approach. If we compare that to, let's say, the fuel cell, we see that the fuel cell, from an overall power plant efficiency perspective, is roughly on par with the conventional thermal engine. And of course, we've got turbo-electric arrangement here. But that's not the only thing we compare, because we're not just only concerned with efficiency, we're concerned with masses as well. So we would compare things like the source gravimetric specific energy, or the energy density as it's commonly referred to as. And we can compare these attributes, and this gives us an idea of the energy content of the given source that we're considering. We would also look at the overall gravimetric specific power of the system. So if we look at all of the power train, the components, the subsystems that contribute this in the global train, what would be the equivalent, let's say, kilowatts per kilogram? And we can compare and contrast all of these. As we can see, for state-of-the-art, the thermal engine approach, of course, looks very good. However, we can see that there are some attributes of the battery base that could be useful, that could be interesting as well. If we shift over to year 2035, what we can see is, yes, the thermal engine still has very desirable attributes, but if we look at, let's say, the full turbo-electric and the E-chain battery, we start seeing the emergence of much more desirable characteristics. So, with such a very simplified study, we can use it as a means of offering logical rationale for our down selection. We can say the following. Based on this, for UAV type application, drone type application, something like a turbo-electric arrangement, a partial perhaps turbo-electric arrangement, but hybridized with electrochemical source could be of interest. Here's another study that we've conducted at Safran, a generic study looking at VTOL type applications. We've got two categories here, what's called the multi-copter, and we've also got a compound tilt wing arrangement. And in this particular trade study, what we're interested in is looking at different scenarios. So for example, an all-electric approach, assuming a lithium ion versus a lithium sulfur, or we can consider a turbo-electric arrangement as well for both of these categories. And I should note to you that there is indeed a difference in speed when we compare and contrast the multi-copter versus the compound tilt. That's the whole reason for the compound tilt. But what's interesting here is that when we perform the trade study, what we find is the all-electric solution for both types of aircraft morphological solutions. The all-electric solution seems to top out at around 20 nautical miles for 4 passengers. Now, it's really up to the market to decide what the technical specifications should be. If the market decides that a one-hop, 20 nautical mile, 4-passenger, approximately 900-pound payload scenario is sufficient, then perhaps the all-electric approach would look feasible. If, however, the market decides a multi-hop capability that perhaps has a capability of doing 3 or possibly 4 hops, well, these type of simplified trade studies tell us that the turbo-electric arrangement, perhaps hybridized, looks much, much more interesting as opposed to the all-electric arrangement. Again, this gives you an idea of what we could do in terms of looking at the different scenarios in simplified studies and making big decisions and conclusions for purposes of down selection. Now, those 2 parametric descriptors I talked to you about previously, degree of hybridization for useful power, degree of hybridization for energy, through a lot of math, theoretical work, one can connect the 2 parameters together. They are not linear in nature. This connection between the 2 parameters is actually non-linear in nature. We can produce a set of curves that you see here, what we refer to as onion curves. So on the abscissa, we've got the degree of hybridization for useful power. On the ordinate axis, degree of hybridization for block energy. And what we can do is we can look at the various studies that have been conducted and get an appreciation of where they sit on such a map. One category of hybrid electric that we know of is what I refer to as the autarkic. Autarkic is the word is taken from economics. It means self-sustaining. So autarkic in our context here for hybrid electric propulsion would mean an ability to recharge during the operation of the aircraft. So you deplete the battery to some state of charge minimum threshold, and en route, whilst the aircraft is performing the operation, a recharge would occur. And these are two examples I show here with Rolls-Royce, as well as a study that we did in Safran. But it gives you an idea that the degree of hybridization for useful power. Now, the next category here would be a mix of series and parallel arrangements, and which has been essentially focusing on regional as well as, excuse me, short to medium range applications, and I've included the Project 804 as part of the cadre of candidates here. We get an idea that the degree of hybridization for useful power can run between 0.2 to up to about 0.5, and the degree of hybridization for energy all the way up to about 0.2. Another category which was shown by Philippe was the partial turboelectric arrangement. Again, motive power, let's say a good proportion of the motive power for the aircraft is delivered by the traditional thermal engine, but of course we have a significant fraction that's also delivered by the electric propulsive device as well. And these are three examples here of Safran as well as NASA, two NASA examples here, the Stark ABL as well as the Maxwell. And we get a feel here, it's something like 0.4 to 0.5. Degree of hybridization for energy is 0 because it is a turboelectric arrangement. The full turboelectric examples here have focused, let's say, on the very large aircraft, blended wing body. We've got the Airbus Rolls-Royce Deep, as well as the Rolls-Royce distributed open rotor, and then of course AERO turboelectric split wing arrangement. We saw an example of that previously as well. Hybrid full turboelectric examples would include the Zunum, right? So the 12-passenger Zunum is a full turboelectric arrangement that has been hybridized with some sort of electrochemical source. And one example for Safran is the hex rotor concept. And then finally, the full electric examples one could cite here is the NASA Scepter, so it's essentially a full electric version of the Maxwell, the original concept that came from NASA. We've got the ONERA Ampere, as well as the Airbus Voltaire and the Bauhaus Luftfahrt Sealiner. So I just wanted to give you an idea, what does the landscape look when we talk about fixed-wing aircraft, and what kind of degree of hybridization for power and energy we're talking about. The ones that are in the middle there, degree of hybridization from 0.3 to 0.5, and a degree of hybridization for energy up to about 0.2, they deliver around 10, 15% reduction in block fuel. The lower degree of hybridization for power solutions deliver in the single-digit percentage, just to give you an idea. Now, what I would like to do is just quickly touch on the notion of safety and redundancy. We heard this from Sylvain when it concerns certification, but from a safety point of view, what needs to be answered is one fundamental question. What constitutes the catastrophic failure mode? We're still having heated discussions and debates within the community about this. For us at Safran today, and I stress it could change over time, when we talk about VTOL application and we talk about fail-safe criteria, what we are essentially talking about are two things. One, the loss of one rotor does not lead to catastrophic loss of the complete aircraft control. So this is absolutely fundamental, particularly if you consider a VTOL application where the propulsive devices not only deliver motive power, forward motion, but it's also used, or to hover, but it's also used to control the aircraft. This is a controlled, configured aircraft. More often than not, if you look at the myriad of concepts that you see there, we do not have the luxury of some sort of passive static stability system on board the aircraft. So this is fundamental. The second aspect is when we talk about the electrical chain, we want to ensure that we can absorb at least 2 points of failure when it concerns the electrical energy source. Again, because of the statement that we do not want catastrophic loss of control of the aircraft with 1 rotor loss, we need to ensure that a sufficiently robust and quite conservative assumption is made with regards to the supplied energy and, of course, the power that runs the particular rotor. There are other questions. If we have multi-rotor system and we pair these and they're counter-rotating to each other, if one of the rotors are lost, we would have to perform a mandatory in-flight shutdown of a paired rotor that is functioning in a normal fashion. What would be the best combination in terms of laying out the number of rotors, what kind of configuration, and what would be the in-flight shutdown procedure? These new questions emerge as a result of dealing with, let's say, VTOL application, dealing with hybrid/electric propulsion. And of course, following on from that, what would be the constrained optimum power rating when we talk about each of these rotors? Be mindful, again, we're not just talking about sustaining hover or forward flight, we are also talking about ensuring the minimum acceptable level of control, handling qualities expected of the aircraft. In terms of safety and certification considerations, what we need to ensure is that the airworthiness regulations recognize components, systems, subsystems associated with hybrid electric as something familiar and synonymous with the traditional propulsion category that we consider today, that we certify under today. Now, what this means is that hybrid/electric propulsion technologies need to be consistent, need to meet the expectations of what we see with gas turbines today from a certification point of view, so this ensures safety, but also from an operational point of view, this is important because we want to ensure that there is a level playing field when it concerns quality, when it concerns the level of reliability, redundancy, when you mix this technology with aircraft fleet with other technologies. So this is of greatest importance. As a result of this, these novel technologies perhaps still have scope to be embedded within the traditional certification specification E or the 14 Code of Federal Regulations Part 33. We at Safran feel that there is definitely scope to embed it within these and it would sit comfortably within this. We should ensure that any certification that's considered sees this technology as not a technology that serves flight control. I stress this particularly for the VTOL. Hybrid/electric propulsion should be considered the way engines are considered today, which is a source of power for flight of aircraft as well as conversion for non-propulsive systems. Hybrid/electric propulsion technology should be considered the same way. It should not be intermingled with, let's say, flight control characteristics. If we start infusing flight control in the context of hybrid electric architectures, this is going to complicate life. This is going to make certification very, very difficult. Finally, to round off, I'd like to highlight to all of you that, okay, the engineering work is done. It's challenging, but we're working steadily at that, and I'm quite confident that we will achieve a status where those 4 tenets that I talk about will be fulfilled. Okay, let's assume the airworthiness, the bodies decide to certify said technologies as well. But what is of greatest importance is standardization. Without standardization, there is no way to transform that technology that, let's say, potentially producing a profit that is certified and implemented operationally. To this end, as was mentioned, I'm part of an AIAA working group. we had a task force, and I had the good fortune to lead this task force, where we decided to standardize all of the parameters, figures of merit when it concerns the description of systems, components, architectures, aircraft level assessment, and it was our first shot to standardizing everything throughout the community. The first draft of this document was issued in January. I recommend to everybody, please go to the AIAA site, download it. It's a first draft, it's open for critique. We welcome critique. Engineers should always welcome critique, and your feedback would be most valued. And again, standardization is the means of transforming technology into implementation. With that, so ends my talk. Thank you for your time.
Thank you very much. Thank you. So for the next, I'm going to launch a first question to the panel, and then I'll open up the floor for questions from the audience. We've talked a lot about the aircraft themselves. How do you foresee hybrid electric propulsion affect the airport infrastructure from the first, let's say, introduction of the system over the next 20 or 30 years? If today we have a fully electric aircraft or hybrid electric aircraft with a plug-in system, probably most airports cannot support it today. So how do you foresee this introduction of the technology the next, let's say, 20 years? So maybe start with Sylvain.
Well, as we've looked at the notion of combining various systems, we're going to run into advanced prototypes to demonstrate a first step of integrating those systems. Ideally, we would like those systems to be as autonomous as possible. So after this first step of I'll say, demonstration, potentially future steps could involve the notion of recharging batteries during the course of the mission to potentially alleviate the aspect of impact on airports. Obviously, that scenario is specific to regional turboprop leveraging airports. If we then step back and try to answer this question from an urban air mobility system, well, that obviously entertains a whole different set of parameters. And who knows if that notion of urban air mobility will be a point-to-point or a specific hub-to-hub. So the overall city infrastructure in which those urban air systems are going to be operating will essentially need to define those aspects.
Thank you. And from the European perspective, so Philippe, do you have any comments related to that, or any studies you've done in the past to consider those elements?
So you raise an important point. I would say that on our side at this stage, we haven't really looked at this impact on infrastructure because, as I mentioned, the first point is already to identify which are the relevant configuration for hybridization. And so depending on the configuration, the point you are raising will be more or less important. But clearly, this is something to take into account, and we are currently preparing a project in which we want to look at these aspects clearly.
Okay. Thank you. Is there any question from the audience that you would ask to the panelists? There are two mics, one on each side of the room.
Good morning, very interesting presentations. My name is Andre from ITPS. I'd like to know from the panelists if any of your businesses are studying combined cycle to make the thermal efficiency of the engine better, because today the thermal efficiency is between 30–35% conversion, but if you do a combined cycle, it can go up to 45. It's heavy, it's clumsy, but with the with the start of the hybrid electric propulsion, it may be possible. Thank you.
So, shall I answer? So the question, can you hear me? Can you hear me? So the question regards the improving the thermal efficiency. So fundamentally the question is, how close to the peak Carnot efficiency can we reach? Generally around 60%. When we talk about the overall propulsion system efficiency, what we're fundamentally talking about, and if we consider a series hybrid arrangement, we're talking about standalone propulsive devices, and if we combine those, if we look at the combined overall propulsion system efficiency, there is room for improvement, right? As I showed in the simplified trait study for the drone, if I look at an electrical chain only, it's something like 52% was quoted as the overall chain efficiency, and for the thermal, again, this was for a turbo shaft, something like 25%. So there is scope to improve the overall propulsion system efficiency if we consider series hybrid electric solutions. Now, if we consider a parallel arrangement, now what I can say to you is this, because now we're mechanically connecting the electrical device to the shaft, high pressure or low pressure spool. Studies have shown, and it's not just Safran, but other companies and research institutes and universities, the improvement in thrust-specific fuel consumption is very, very minimal. There is no massive gain in terms of introducing hybrid electric propulsion when we consider the classical dual Brayton cycle. However, one thing I do highlight, hybrid electric technologies for the classical dual Brayton cycle will be important in the future for this very reason. As we start considering much, much larger fan sizes, larger bypass ratios in order to improve the next generation of thrust-specific fuel consumption improvement, as well as equally as important, reducing noise. Those engines need to operate in an environment where the non-propulsive system customers have a very large request in terms of power offtake. If you combine a very large fan, a high bypass fan, with very large mechanical to electrical power requirement, what we find is such engines run into violations of the surge margin. When you spool up, spool down, so when you accelerate and decelerate the engine particularly. So what hybrid electric technology will serve as, maybe not directly improving the thermal efficiency or the dual Brayton cycle, it'll serve as an enabler to allow very high, ultra-high bypass fans that are mated to very high power requirements for the non-propulsive system of future aircraft.
Is there any other comments?
Maybe in line with what Askin has just positioned, one aspect that we're looking at from a parallel hybrid standpoint is to specifically leverage the electrical power in specific points of mission across the entire flight envelope. Obviously, as spoken, this will not necessarily impact the thermal efficiency of the thermal engine, but it may somewhat alleviate some of the boundary condition in which we design, such that if we somewhat require less thermal power at takeoff, let's say, and complement this with electrical power, then the overall design envelope supporting the full mission scope can then be tailored. Again, it's not going to improve the thermal efficiency, but it might further optimize the use of this thermal power on specific aspects of any given mission.
Thank you. Are there any other questions from the audience? Yes?
I'm kind of a simple guy. I'm a master's student, mostly focusing on structures, and I was wondering, you guys are talking about propulsion and all these new aircraft. I was wondering, is there any role for something like structures or advanced materials in these new designs, or is it mostly focused right now in the industry on optimizing propulsion from these types of planes?
In fact, yes, this is part of the degrees of freedom that are offered by hybrid electric propulsion, because you can, for example, when you distribute propulsion, you can use it to try to control the aircraft and maybe size down the tail, the control surfaces. So this is part of the game to try to develop synergies between the propulsion system and the airframe in order to decrease the mass. In another kind of idea, I show the eco concept, and in fact they have integrated the ducted fan, the distributed ducted fan, in the width of the wing. They have what they call a split wing, and in their papers they show that this increase it's improved, in fact, the structural design of the wing and so on, and so they take benefits from this also. So it's really trying to find optimization everywhere in the aircraft.
With regards to the structures, if you recall, we have examples of the NASA Maxwell, the Safran and ONERA, the partial distributed turboelectric arrangement. By virtue of distributing the propulsive devices and, let's say, perhaps the thermal engine at the tips, what we find is the classical wing box is not suitable anymore. Because now what we have is, instead of just the traditional aeroelastic, we now have a problem which is aero-propulsion elastic. And what we find is that the conventional, the traditional morphological layout of the wing box is not proving to meet the requirements that we need, and we're ending up with very heavy wing weights, for example, which is essentially serving to obliterate some measure of the emissions reduction potential of that aircraft morphological approach. So if you're asking what should be the new topic in the structures or materials domain, that would be a fantastic example to pursue and see where you could go in minimizing the amount of structural mass associated with that integrated aero-propulsion solution. A second piece of advice, we're dealing with electrification. And if we talk about structures, you may scratch your head, how can you make a connection? Well, a lot of very excellent work, inroads have been made with regards to adaptive structures, morphing. What is more intrinsically synergistic, if we talk about morphing, that's probably the most intrinsic synergistic approach when we talk about hybrid electric propulsion. And adaptive structures would not only just pertain to, let's say, traditional flight control surfaces or improving the airframe efficiency of the aircraft, but it could also be a technology used in adapting the characteristics of the nacelle, right, of the ducted fan, or manipulating the geometric attributes of the rotors or the blades. So for me, these are the two areas of greatest interest: the distributed propulsion and the wing morphological optimization, and the broader domain of looking at adaptive structures with, of course, advanced electrical actuation technologies.
I have a follow-up question, I think, for all of you. So you mentioned that the benefits of hybrid electric propulsion comes with a synergetic integration with the airframe. How do you foresee in the future having propulsion companies that develop engines, or historically developed engines, and OEMs that develop the airframe? How do you see this collaboration that will go well beyond the attachment points and fuel lines, right, of the engine with the aircraft, where the dynamic properties of the wings coupled with the engine location and all those subsystems? How do you foresee this new collaboration that will have to occur to actually take advantage of hybrid electric propulsion at most?
This is a question for my industrial colleagues, not for research.
Well, obviously, at this point in time, I'll say from many aspects. We've talked about notions of standards and certification. That's clearly one angle with which we're looking at integrated work with the airframers. Another aspect will obviously have to do with mission management. In some optimized, I'll say, platforms, we're looking at trade-offs in terms of range and potentially passengers to the benefit of overall cash operating costs, COC. And this is where, from a business case, as Askin mentioned, as adopting to the further needs of aircraft and missions, this whole aspect of optimizing systems with the notion of trade-off is a second aspect in which we're working. Maybe a third angle we're also looking at, and you pointed out earlier, David, the notion of infrastructure. Obviously, for us, proposing a propulsion system with new requirements in terms of potentially battery interchange and the like is one aspect. How will the airframers manage the overall mission envelope, including services potentially required at airports, is a third angle. So obviously, it creates a more holistic approach in terms of the overall mission than specifically related to propulsion, as we typically used to do in the past.
Thank you.
My take is the traditional classification of professionals, we need to rethink this. Today, one calls themselves a propulsion engineer, or a structures engineer, or, I don't know, electrical systems engineer, or technical person. I don't want to exclude anybody here. Now, the thing is this, we're talking about highly closely coupled airframe propulsion solutions. Now, to that end, those type of solutions cannot exist within the framework that we've defined how we do business in the industry, how we educate, how we conduct business, how we operate. I cited one example. Instead of calling yourself an aerologistician or a structures engineer, structural engineer, what we need to do, and I really would like to ask the academic community here to think about this, perhaps to rethink the syllabus, the curriculum, such that you start producing a classification of professionals referred to as aeropropulsive elasticians. Or, instead of propulsion engineers, aero-electrical propulsion engineers. So what I'm talking about, I'm not just harping on these particular categories and we should name them as such. What I'm talking about is the days of single discipline. That is gone. It is gone. We need to recognize that individuals now must juggle as part of their job and be familiar with and be comfortable with juggle, say, 3 different disciplines concurrently. This challenge needs to be met by the academic community in terms of providing education. And the hope is, when we start producing the first cadre of such people, the solutions that we've presented to you today, we could perhaps even go further and squeeze extra performance and more emissions reduction with hybrid electric propulsion technology.
Thank you. Philippe, do you have any comments to add on that?
No, as I said, as research, we are not really dealing with this industrial organization. It's clear that, as I said in my presentation, the design of the propulsion system is fully integrated with the design of the aircraft. So, from my perspective, I guess it changed something in the industrial organization, but I'm not an expert in this field. I will not say for industry.
I'm just going to repeat the question for everyone. So the question was about using nuclear energy as a replacement for the battery that is quite low energy density.
So I would say with nuclear energy, I'm afraid that the problem of the mass will not be that much smaller than with batteries, because it's something to have nuclear sources, but then you need to have all the protection systems around to protect people in the aircraft. I remember I've been also working for space in the past, and I remember this project of nuclear propulsion for spacecraft, in which you had a long structure between the engine and the capsule where people were. It was maybe 30 or 50 meters long in order to separate people from the radiation. So I'm afraid nuclear is maybe, without taking into account all this issue of the multiplication of nuclear sources, dissemination, if you have a crash, so no, definitely I think there are much better solutions to look at than nuclear.
So we're coming to the end of this panel. So just in a few words, when do you think we can ride a commercial hybrid electric aircraft that will be on the market? If you have a prediction to do today, what year will it be?
I think it's risky to say. I think we need research, and after, when the technology will reach the right TRL for considering development, also the development will be very different from the development of a current aircraft. So also the development of the aircraft will probably be longer than designing the A350, because the A350 is not that different from the previous one. So I would not see that before 2040 at least, but even like that, I think, and at the same time, we are in a very difficult situation, because I mentioned this curve of ICAO showing the increase of the aviation emission, and we all know that we are in a very urgent situation, because if we want to meet the COP21 targets, we need to reduce drastically emission by 2050. And taking into account the time required for the aircraft to be bought by airlines and to go inside the fleet, we see that we are definitely facing a very big challenge, and probably in the meanwhile, offsetting will be the only solution, probably.
Well, thank you. And from your side, in just in a few seconds, what do you think would be?
Well, I'd say that this is obviously a very broad question, but could it be answered from potentially an aspect of mission and range size? I've talked about Arbor Air, who came public with transforming Beaver into fully electric. Well, that could be something that could happen between the 2030s. But we're looking at 15 minutes up and very limited passengers. So that's a set of requirements that might be conducive for an earlier introduction. Anything beyond this, obviously that's me, Sylvain, saying, I think that it's beyond the 2030 range easily.
With regards to general aviation, and this depends on how serious the on-demand mobility movement is as well, but it's conceivable 2020s we'll see a whole lot of general aviation aircraft that are essentially running as all electric. If the VTOL technology, the on-demand mobility technology, proves itself, and I should highlight to you what will be this is controversial I suppose, but what would be the enabling technology for on-demand mobility, and I apologize to my technical colleagues here who deal with motors and power electronics and so on. It's not the engineering, it's not the hardware, it's the autonomous operation capability. If our computer scientist types can figure this one out, and you have the ability of essentially with as much know-how to drive an automobile, you could fly an on-demand mobility vehicle, If this happens, the cascade effect in terms of investment in engineering development will definitely accelerate. And my feeling is, if this occurs, in the 2020s, we will see a whole lot of all-electric aircraft buzzing around out there. Now, with regards to commercial transports, perhaps we'll see one or two interesting demonstrators. Perhaps we'll see one exemplar, let's say a 19-passenger aircraft in the late 2020s. But in all honesty, when we talk about commercial, we're really talking about beyond 2030, right? And as I indicated a moment ago, an enabling technology for these ultra-high bypass fans would be something like parallel hybrid arrangements. So it is conceivable to a lesser extent that hybrid electric technology could make its way in the 2030 plus time frame.
I would like to add something. I think we should also take into account the fact that such developments, which are quite disruptive, will probably require that there are some policy that encourage people to go in this way, because we have not mentioned the market aspect, but for example, the open rotor, it is said that it has been also demonstrated that it can save 15% or something like that, but it's still not really considered for introduction because you have other aspects in the market. And going to such disruptive systems for which we don't know about the cost, because for the time being, it's very difficult to say what such aircraft will cost, and it's not clear that they will be less costly than aircraft we have today. And so all these things can only happen if there is a policy driver or maybe a cost driver. If the cost of crude oil increased drastically, maybe it will push in this direction. Otherwise, it will require policies, I think.
Well, please join me in thank the panel for this very interesting talk. Merci.
Thank you. Before everybody leaves, well, before those of you who are still here leave, there is a missing laptop case